Hey guys, today we're going to talk about chi-square testing. I'm just going to run through two examples with you of different chi-square tests, and then you have some practice problems. So these are just a little notes on what we're doing. Chi-square tests are for categorical data. So every hypothesis test that we have done up until now has been for quantitative data, whether it be for proportions when we had the counts out of a total, or for means. But now this is for categorical. So remember, categorical data is a word describing a characteristic like gender, part-time, full-time, type of seat on an airplane, whatever. A couple things about a chi-square distribution before I do these examples. There's no negatives because we're talking about counts, so you can't have negative counts. I'm not going to have negative people with blonde hair. It's asymmetric, so it looks like this weird little thing. There's a longer tail to the right. Area under the curve, still 1. With a higher degree of freedom, it still is going to approach a normal curve. So as you can see, degrees of freedom 3, it like looks like that. But as I increase, this left side here is getting a little kind of out there a little more, and it's turning more to a normal curve. We look at it with this chi-square here. It looks like an x squared. It literally looks like a capital X squared. And defining degrees of freedom, we're going to do categories minus 1. So if we're talking hair color and we're looking at red hair, blonde hair, and brown hair, that's 3 categories, so our degree of freedom would be 2 for 3 minus 1. Okay, so we're going to look at 2 examples today of chi-square tests, and we're going to do another one next time, and I'll show you calculator stuff. So here is an example of homogeneity. Homogeneity is when we are looking at all of the categories to have the same amount of, we expect them all to have the same amount of people, whatever it is. So in this case, if I suppose I generate 100 random values between 0 and 10, and I construct a frequency table with 10 classes or 10 bins of width 1, if the random number generator is working properly, how many would I expect in each class? So if I'm going to do random values between 0 and 10, and I'm going 10 classes of width 1, so with the 10 classes and the 100 random values, I could expect 10 to be in each one, because the 10, 100 divided by 10. So there are my classes, just random 1 through 10 bins, and those are just observed. So that's just the data that I got from whatever this sample is. Our expected is 10, which is the same across the board, which makes it homogeneity because we expect them all to be the same. With the 10 different categories, my degree of freedom is 9. From there, I'm going to go through this chart, and it's going to lead towards our chi-square test statistic. If you take a look at your formula sheet, so pause me, go get a formula sheet if you need to. On the blue one, all the way on the bottom, it has your test statistic formula. It's the summation of observed minus expected squared over expected. That's what I'm getting to in this chart. This is me calculating the test statistic by hand in this chart, because we can't do statistic minus the null or statistic minus parameter because we don't have any statistic. We're looking at how many numbers are falling into a class. And we're looking at, we don't have like an average numbers. So we have the observed minus expected. That expected is kind of like that parameter that we talk about. But anyway, so to continue to calculate observed minus expected, I just subtracted them. Next part is I squared them. You might remember that I did a chart like this when we did standard deviation. By the way, feel free to pause me as you're doing this. I'm just going to keep talking through it. and then over the expected. Okay, so at the end, it's the summation of them, so I need to find the sum of all these. So when I add all of these up, that gives me 10. That's nice. It worked out nicely. I did that on purpose. So there is my lovely test statistic. Here's my chi-square. Here's that formula all the way on the bottom. Equals 10. That's what I'm looking for. That's my test statistic. Okay, please remember, a chi-square test is always one-sided. That makes our life so easy. We don't have to worry about subtracting from 1 if it's on the wrong side. We don't have to worry about multiplying by 2 when we get to our p-value. It's always one-sided because everything is positive all the time. Our hypotheses are also pretty simple. They're going to be in words. So our null, all categories will have the same proportion. So all the categories, 1/10. You could also say all of the categories are the same. You could say the random number generator is working properly to put it in context. But remember, our null is always that everything is good. Everything follows what we think it follows, and the alternative is testing against that. So they're not evenly distributed. All right, conditions are a little different because we don't have the same kind of data, so we can't use the same conditions. We can't use, oh yeah, 30 is greater than n is greater than 30 for the central limit theorem. Well, we don't know that, so we don't have enough. We have different kind of data, so we can't use the same conditions since it's categorical. So first one is counted data. We want every category to have counts. So 5 people have red hair, 5 people have blonde hair, whatever it is. Counted the number of digits in each category. So in each category, in each of those classes, we counted the number of digits that fell into those classes. By the way, those classes, I mean, with the 1 to 10, could be, or the class numbers, 1, 2, 3, all the way to 10, could be 0 to whatever. It's just, those are just categories that we're looking at the numbers falling into. And the 1 through 10 are just names. The next one, randomization. Random number generator was used. That's it. It literally is a random number generator. So we still need randomization because we still need to be able to generalize about a population. And expected cell frequency. We need our expected values to be bigger than 5. This is similar to our large counts condition as well as our central limit theorem. We just need to have enough. That's all. Since the conditions are met, we will use a chi-square test of homogeneity. So that's me naming my test. You could have done it earlier too. Doesn't matter where you put it, as long as you put it somewhere. All right, calculations. Find chi-square test statistic. So this is straight off your formula sheet. Okay. This is me 9 minus 10. That 9 is from your observed, go look at your observed chart. Minus 10 squared over 10, whatever, all this stuff. We already did this. You can use the chart as your calculations. Or you can do this with the dot, dot, dot. It's 10, which we got up top. Degrees of freedom is your number of categories minus 1. So 9. We had 10 classes. Minus 1 is 9. And then we sketch. It's a rough sketch. It's okay. This 10 is our chi-square. P-value. There is a chart, but it's not always going to be easy to find on your chart. If you look at it, it is table C, so feel free to look at table C. But it doesn't have all the values that we need all the time, so our calculator is usually easier. If you go into your calculator and um, this is in, let me type this here. This chi-squared CDF is in your distribution menu. And that is in the statistics. So wherever you find the normal CDF and the inverse normal and the t-CDF, there's also a chi-square CDF. It's going to ask you for your lower bound. Well, it's always one-sided. So your lower bound is always going to be your test statistic. And you're always going to put a big number here. You could put 10,000, you could put 100,000, whatever. And then your degree of freedom in our case is 9. So that's where this p-value is coming from. Okay, let's remember that our p-value here is greater than our alpha. I honestly just couldn't type it on this. That's why I wrote out the word alpha, which is 0.05. So I fail to reject the null hypothesis. There's not enough evidence of the number generator not working. So there's not enough evidence for the alternative. Please stop saying we're accepting things. We're never accepting. We're failing to reject the null or we're rejecting the null. Okay, the other one we're going to look at, oh, I didn't draw boxes, that's okay, is take a look at the back. This is going to be a goodness of fit test. Super, super, super similar to what we just did. And pause me if you need to go back. You might want to pause me and do the practice problem that goes with that last one, and then make sure you're good, move on, totally you. So I've got these flowers that are producing these 3 different colors. Don't ask me why I use weird colors, but I did. In this ratio, 6 to 3 to 1. This means that magenta is 60%, 30%, 10%. Total of 100 seeds are planted and all germinated, yielding, this is weird, the following results. So here we go. This is what they got. This is what's expected. This is the difference between homogeneity and goodness of fit. Homogeneity, all these guys, they'd all be the same. Goodness of fit is we're looking at it to fit a given ratio. That's the difference between the two. Everything else is the exact same. So if you want to pause me and try it, you can. If not, keep on listening. Oh, I did do boxes. Huh. All right. So I'm going to do this chart. I'm just going to lay it out a little differently. This way you can see 2 different ways that you could do a chart. Categories, observed, expected, and then this is running through that test statistic form. So start out here. If I have my magenta, observed 52, I expected 60 because I expected the 60% from the 6 to 3 to 1. Subtract, it's cool to get a negative. That's why we're squaring, so we get rid of those negatives. And divide by expected. So when I go through and do the rest, here they are. And then I add them up. There's my test statistic. Like I said, guys, I'm going to show you how to do this in the calculator too. Next time we are together. Okay, so complete the hypothesis using alpha of 0.1. I did it on purpose because we're getting, don't get me wrong, 0.05 is usually the case. However, if they tell you to use another one, you have to use it. You can't just use 0.05. So make sure you're just reading it, just to be safe. Okay, same concept as last time. Null is we're all good, alternative we test against. K equals 3, that's my categories. Null, all proportions are as reported, or as they should be. All the proportions follow the given ratio, any of those things. We're good, everything is following. Alternative, at least one is different, right? I mean, we could still have 60% for the magenta, but if the other 2 don't match, it doesn't follow it. Okay, just keep in mind, null and alternative, your null is whatever, your alternative is that the null is not true, so at least one category differs from the corresponding hypothesized value. All right, so conditions. This is for a goodness of fit because we're looking if it fits the ratios. So count of data, number of flowers of each color is given, right? It's a count. There were 52 magenta. That's a count. Assume that the 100 seeds used represents all the seeds because we're just assuming that we're just assuming that it's random. We're assuming that they can represent all the seeds because, I mean, it's flower seeds. I'm assuming that they're just random in the package. Expected cells, the 60, the 30, and the 10 are greater than 5. You do have to state the expected. So tell me what the expecteds are. If you did use a chart, you're more than welcome to write C chart if you put them in the chart already. But you do need to show somewhere what the expected values are, whether it be here or in that chart. Okay, test statistic we did in the chart. Here's my lovely formula. And there's my work. Degrees of freedom is 2 because I had 3 categories, 1 for each color. So there we go, degrees of freedom. P-value, that's coming, I'm pulling that with my chi-square CDF. So I put in my chi-square CDF, 2.667 was my lower bound. A positive 1,000 is my upper bound, and my degree of freedom is 2. So there's my p-value. Okay. Find your p-value in sketch. P-value is the area to the right of chi-square under the df equals k minus 1 chi-square curve. There's calculator commands. And then our statement. So we're going to reject the null. If there is evidence to conclude, remember to state your conclusion in terms of what the data means, rather than making a statement about the distribution of counts. So tell me what this means. Or you fail to reject, so there is no evidence to conclude. Just be specific to the problem. That's kind of what I'm getting at here. Don't just write there is evidence to conclude, or there is evidence against or for the null hypothesis. Be specific to the problem. So notice how my first couple steps were the same as the previous step, so that kind of makes life easier. And our expected equals n, a number. It's our hypothesized proportion for each category. So our expecteds are the 60, the 30, and the 10. That's the only difference. So let's remember that. So in our case, our p-value is 0.2636, which is greater than our alpha of 0.1, so I fail to reject the null hypothesis. There is not enough evidence to conclude that the flower proportion are different from the 6 to 3 to 1 ratio. So this is for our, we're kind of writing in terms of our alternative. We fail to reject the null, not enough evidence to conclude that the flower proportions are different than 6 to 3 to 1. Okay, so 2 practice problems. Get from the sub. So here's the first one. We have a car dealer takes a random sample of 60. Does it indicate that customers prefer some colors to others? So you are looking at the null being they don't prefer it. So they all should all be the same, evenly kind of distributed. So that'll be a test of homogeneity. This one's the next one that I believe is on there. They're following this distribution. That's why it's a goodness of fit test. So try those. Check your answers in Google Classroom. If you want to look at a few of these, this is just practicing with chi-square CDF, which I think we're okay. Other than that, that's all I have for you. Feel free to pause me, rewind me, do whatever you need to do. And that's all your only homework. So you just have to finish this, and that's it. If you want to try those practice problems, feel free. we're going to come back together and do one more test for chi-square, which is, again, super similar. And then that's it for categorical data. So kind of a little easier, a little less work. I will show you how to do it in the calculator so you don't have to use the table, but the table kind of lays it out nicely as we're starting. Okay. All right. Thanks, guys.